All right, in this video we get to finish up our final discrete probability distribution. So this will be the very last lesson from chapter 5, and we're going to talk about something called the Poisson distribution today. So we've tackled a lot of them. Most recently we did the geometric and the binomial, and the Poisson is actually related to those two. So we will move on after this. We're not completely done with probability distributions, but after this, we'll move on to something called the normal distribution in chapter 6. So without further ado, as you can probably guess, the guy right here is the inventor, if you will, of the Poisson distribution, and he aptly named it after himself. This is Simeon Denis Poisson. He is from France, if you didn't already guess that. He was obviously a very good mathematician. He has a quote here. Let me find it. Here it is. All right. So in his eyes, he says, life is good for only two things: doing mathematics and teaching it. So very much love teaching math and doing it as well. So probably don't agree with that statement, but in his eyes, that's what life was good for: math and teaching math. All right, so what's a scenario where we use the Poisson distribution? All right, so an experiment where we would use it is generally any probability event that occurs over a period of time. So when the problems that we're going to be looking at, all of them are going to occur over this period of time with some conditions, right? Not any probability, I shouldn't say that, over a period of time, but with some conditions. So basically, it's going to be a binomial experiment that occurs over a period of time. The goal in doing this is to compute the probability of R occurrences in a given period of time. So what's an example? Well, let's say what's the probability of having, let's say, 5 stats assignments in a given week. So that's the time portion in a week. So any given week, or we could say next week. Okay, let's just say next week actually instead. Given that you are assigned an average of 4.2 assignments per week. So if I went through and added up all of our assignments, divided them the amount per week, and we found that there was 4.2 stats assignments every week, what's the probability that you're going to have 5 stats assignments next week? Or what's the problem you're going to have 3 stats assignments next week, or 1, right? It'd be pretty rare to have only give you 1 assignment, but it is possible, right? So Poisson experiments really have 2 elements. They have a time element, and they have always going to be given an average amount. So we always have to have sort of a baseline, an average baseline. And we're going to compute the number of R occurrences. So think of this as like a success or failure over a given period of time. And we have to know some extra information. We have to know an average amount. These events, like the binomial and the geometric, must be independent, meaning, I guess in the case of this example, one assignment doesn't depend on the other assignment. So whatever's happening, it can't depend on the previous one. Each one has to have equal probabilities and only 2 outcomes. So these are kind of the assumptions that we've had the last couple distributions: independent, equal probabilities, and only 2 outcomes, sort of success or failure, or assignment, no assignment. Let's say, what is the probability of it raining exactly 5 times in a week? We can also expand this to like less than 5 times or more than 5 times or whatever. So these are scenarios where we'll be using the Poisson distribution. So there is a formula for this. I'm going to show you the formula. I would like you to at least try to use the formula some. I'm also going to be showing you the calculator instructions on how to do this. Most of the distributions do have calculator shortcuts. We haven't always used them, but I am going to show you on this one how to do that. And hopefully you're able to follow along with that. All right, so let's go ahead and jump into the formula. Now, you're going to be a little freaked out because there's going to be, well, there's not going to be any numbers. It's just going to be all letters and Greek letters. All right, so here it goes. So the probability of R, meaning the probability of R occurrences, is equal to E to the negative, and this little symbol here, I want you to take a second and see if you can figure out what that symbol is. So it's this symbol right here. All right, so it's E to the negative. This symbol is called lambda. E to the negative lambda, lambda to the R over R factorial. And you might be thinking, man, what have we gotten into here? We got no numbers, like I said. We got exclamation points. We got E's. We got these other weird symbols. And this is something we're supposed to use. Well, yeah, congratulations. You made it to this point of math. Good job. All right, so this is our formula. What does it all mean? All right, we should probably tell you what all these different variables represent. So let's go ahead and do that. So the first thing is the E there. That's kind of new, right? So E is just actually a mathematical constant. If you look on your calculator, you'll probably see it's with the ln. You see an E to the x. So that's what we're talking about. If you hit the second and then E, and if you just put it into the first power, E is actually just an irrational number. It's approximately 2.71. It's an irrational number. It's a constant that we use in math. It's the exponential constant, if you will. And it's 2.718, and then it just continues to go forever because it's irrational. All right, so that's just actually a number. On your calculator, you're just going to put E. You're not going to type in 2.71. You're going to put E. Okay, the lambda, that actually just represents the average or the mean. It's the kind of takes the place of what we used in our previous section with the mu. For whatever reason, Poisson distribution, you just use lambda in most cases. I have seen it where you actually use mu instead, but our book uses lambda, and a lot of places use lambda as a symbol for mean. So it just means the average. And R represents the same thing it has been, and that's the number of occurrences. Same thing it's always represented it. And then, of course, the exclamation point is the factorial symbol. And if you remember with that, if it's like 3 factorial, that equals 3 times 2 times 1. So you can go home and tell your, I don't know, whoever that this is what you learned in math. Yes, this is English, kind of. But all right, so that's how it works. What I want to do is let's go ahead and look at one problem using this formula, and then I'll come back and show you how to do this on the calculator. So we're going to sit. All right. So we've got a fire station. On average, this fire station has a call-out rate of 2.2 every 3 hours. So every 3 hours, they get an average of 2.2 call-outs. So using the Poisson distribution, find the probability that in any period of 3 hours, there will be 1 call-out or no call-outs or more than 4 call-outs. So let's start with the probability of 1 call-out. All right. So a couple things we'll need. We need a lambda. Lambda, again, represents the average. So there's 2.2. And I'm going to write out the time here as well, 2.2 every 3 hours. Because that's important. As we do some more problems, it won't always be the exact same here. This is 3 hours and this is 3 hours. It's important that those are the same. If not, we're going to have to modify our lambda a little bit. So in this case, we're actually good because we're looking at a period of 3 hours for our probabilities. So we want to know the probability of 1, because 1 call out. So really, all we need to know is R. R is going to change in these, and lambda, and everything else actually stays the same. So the probability of 1 is going to be e to the negative lambda, so e to the negative 2.2, and then lambda, so 2.2 to the r is 1, over r factorial, so 1 factorial. So then, plugging this into your calculator, I always like to just put parentheses around the whole top and the whole bottom when you type something in. It's a good idea to just type it in all at once. So e to the negative 2.2 times 2.2 to the first power divided by 1 factorial. 1 factorial is just 1, but if you can't remember where that factorial is, remember you hit math, and then you go over to PRB, PRB, and then it's the number 4 there. 4 thing. So divided by 1 factorial, and we get 0.2437. So about 24.4%, if you will. All right. So there's about 25% chance that we're only getting 1 call out in the next 3 hours or so. So we could also do the same for no call outs. So the probability of 0 call outs is going to be almost exactly the same. The only thing that changes is R. So e to the negative 2.2 times 2.2 to the 0 power over 0 factorial. Now don't make the mistake with that 0 factorial and thinking it's just 0. 0 factorial is equal to 1. So don't make the mistake it's 0 and then it's undefined. No, 0 factorial is actually 1. So if we go ahead and type that in, and we're going to get 0.1108, or approximately 11.1%. So just over 10%, there'll be no callouts. All right, now, next one, the probability of more than 4 callouts. All right. So this is a situation, probability that more than 4. Or you could say the probability of greater than, so you could say R is greater than 4 would be the better math way to write that. So probability that R is greater than 4. So this would be a bit challenging because theoretically, all I'd have to do is the probability of 5 plus probability of 6 plus probability of 7 plus probability all the way to infinity, right? Until our probability gets basically be nothing. Okay, so that's not reasonable. There is an easier way to do that. That is the probability of 1 minus, and then 4, okay? Probability of 4 plus the probability of 3 plus the probability of 2 plus probability of 1 plus probability of 0. So we did 1 minus all of those probabilities. This is called the complement. Okay, we've talked about this strategy a couple times. We do 1 minus that will give us the correct answer because it's the complement or sort of the opposite of it. So we found all of these probabilities and then did 1 minus all of those. That would give us the correct answer. That is a lot of work, and you had one or two like that on your quiz where you had to do all these. There is a shortcut on your calculator that we can do this, and that is what I'm going to show you next. And I'll show you how to do these single value ones as well. So let's flip back. Here are your calculator instructions. I kind of put all the different scenarios for this. It really isn't that difficult, but it can be just a little bit confusing if you've got less than versus less than or equal to. So you kind of got to interpret the problem in that way. But if we're looking for just a single value, it turns out this is pretty easy to do. All you're going to do is on your calculator, you're going to hit seconds, and you're going to hit the vars number or key vars, which the blue there is distribution. So second, and then we want distr, which is the vars key. Now distr, that represents distribution. So that's talking about probability distribution. So you hit second distribution. You'll then see a screen where it says like normal PDF, normal CDF, env norm, env t, and some more things. We're going to scroll down. Scroll down till you see you'll actually pass binomial. You'll see binom PDF, binom CDF, and you'll actually also see geomet. So that's binomial and geometric. But we want the Poisson, so we're going to do Poisson PDF. So Poisson PDF. All right, Poisson PDF. All right, and then this is pretty easy. So we're going to select that Poisson PDF. It's going to ask you for a lambda value. And so all you do is type in your lambda and x value. The x represents your r, x, which is your r value. You just type those in, and then you hit paste. And it does it for you. Paste and enter. Probably figured it out at that point. Enter. That's it. So we just go to Poisson PDF, type in what it asks you for lambda and asks you for the x or the r value. You hit paste and then you hit enter. That's it. So if we were to go back and try a couple of these real quick, probability of 1. So we're going to do second distribution down to Poisson PDF and lambda in this case is 2.2. So I'm going to type that in. Be a good idea if you did this as well. My x value is going to be 1. Then I'm just going to hit paste and then enter. And what do you know? 0.2437, same thing. So this is Poisson PDF. And then I'm just going to type in my lambda 2.2 and 1. That's what it should show up like when you paste them in there. It should say Poisson PDF 2.2 comma 1, enter, and you'll get the same answer. This one will be the same thing, Poisson PDF 2.2 comma 0, and you'll get the same thing. That's it. So very simple once you figure out where the key is. Now it gets a little more complicated when we have like a more than or less than. Okay, we use a different key. It's right below it though. We're going to be using the Poisson CDF. So you get there the same way. I'm not going to rewrite that step, but it's going to be the Poisson CDF. And I'm actually going to do this less than or equal to first. So less than or equal to, we're just going to do Poisson CDF. That means cumulative distribution frequency. So C is cumulative. C equals cumulative. So we're going to do Poisson CDF in that case. So that's less than or equal to, meaning it includes the value. So if you go ahead and do Poisson CDF and just click on that, it's going to ask you for the same things. So you're going to type in your lambda and your x value. Okay, so you're going to have your lambda first and then your x value. This x value is the x value and everything less than it. It includes the x value. So it's a little bit challenging because if you're doing less than or equal to, it works perfect. All you do is Poisson CDF, lambda, and then the x value, and that will give you, so you're looking like 3 or less, then you would just type in 3 there. And what it's going to do, it's going to add 3 plus 2 plus 1 plus 0. It does all that for you. You're just going to type in 3. However, you have to think a little bit differently if you're thinking just straight less than. You're going to do Poisson CDF again. You're going to do your lambda. But if we want less than but not including that value, we're going to actually type in our x value minus 1. So if it was 3, then we're going to actually type in 2 because we don't want to include 3. We just want to include all numbers less than 3. Okay. And if we're thinking greater than, we're actually going to be doing the complement in this case. So greater than and greater than or equal to is going to be just a little bit different. So we're talking about just greater than, we're going to do 1 minus Poisson CDF, and then lambda, and then the x value. So we do want to actually include the x value in that one. And if we're doing greater than or equal to, it's 1 minus Poisson CDF lambda, and then the x value minus 1. All right, and I'll explain that a little bit more here as we do some more problems. So that's the general, just the formulas you're going to be using there. Let's go ahead and tackle this last part. So more than 4, probability of more than 4. So this is just a straight greater than, if you will, right? More than, greater than, same thing. It doesn't say that number or more, just says greater than. So we're going to do 1 minus our Poisson CDF. So we're going to do 1 minus Poisson CDF. On your assignments, if you choose to do the calculator for all these, I do want you to write out the calculator, what you typed into the calculator. So if you're doing the Poisson PDF, then you need to write out what that is. And if you're doing Poisson CDF, write exactly what you did. Okay. And then, so for our lambda, still going to be 2.2. And then it's more than 4 call out, so we're going to make 4 our value. So it's going to be that simple. I'm just going to type 1 minus second distribution, Poisson CDF, lambda is 2.2, x value is going to be 4, paste, enter, and we get 0.0724, so that is 7.2% chance. So pretty unlikely that there's going to be more than 4 callouts. 2% chance. And we'll practice a few more of these, so don't get discouraged if you're struggling thus far. Let's go ahead and look at our next problem. All right. I think we're skipping one. All right. The number of cars passing a single point on a country road has a mean of 1.8 per minute. So maybe you live on a country road and you're sit there for an hour or so and count how many cars come each minute. The average ended up being 1.8 per minute. So using the Poisson distribution, find the probability that in any 10-minute period there are 2 cars, 5 cars, or less than 10 cars. All right. So let's go ahead and tackle that. So first thing we want to identify is our lambda. It's our average. It says an average of 1.8 per minute. Now the question asks, find the probability that any 10 minutes. So we're actually going to be modifying our lambda, because if it's 1.8 per minute, we want to find the probability in 10 minutes, which means we need to multiply this by 10. So times 10 gives us 18 per 10 minutes, because we're thinking about the probability for every 10 minutes. So 18 per 10 minutes. So that is going to be what we want. Lambda equals 18. On the problems in your book, you do have to modify this to fit the right interval, because we need these 10 minutes has to match in this 10 minutes. If these are not the same, then you got to change your lambda to match it. Whether it be multiplying or dividing, you'll have to change it. All right, so any 10-minute period, there are 2 cars, 5, or less than 10. So probability of 2. If we write out the formula, that's e to the negative lambda, so e to the negative 18, and then it's lambda to the r. So r is 2 over 2 factorial. So let's try it that way real quick first. E to the negative 18. Don't forget that negative with that exponent up there. I forget that sometimes. So lambda squared divided by 2 factorial. And I think it's going to be a pretty small number. Yeah, super small. All right. It's very rare that you would only see 2 cars in 10 minutes if you're almost getting 2 in every 1 minute. But it's an important point, because I've noticed that some of you guys struggle with writing out these calculator outputs. So this says 2.467 blah, 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 e to the negative 6. So what this means is times 10 to the negative 6. So I have to move my decimal 6 places left. Move decimal 6 places left. So move it 1, 2, 3, 4, 5, 6, and it will give me with 5 zeros. 1, 2, 3, 4, 5. Gives you 5 zeros because the first one's going to move in it just to the left, and then you got 5 more times, so you're going to get 5 zeros there. It's a very, very small percentage chance, right? So it's 0.00002. This would be equivalent to move it 2 places back to the right, 0.0002%. It's a very small chance of that happening. If we did the probability of 5 cars, actually, let's change this to 15 cars. Might be a little more interesting. Probability of 15, lambda still is negative 18, and our R then would be 15. So it'd be e to the negative 18, 18 to the 15th over 15 factorial. So let's go and type that in real quick. 18 to the 5th divided by 18 factorial. And that's a pretty small number as well. All right. That's even smaller, actually. All right, I'm actually not going to write that one out because it's really small. It's 4.49 e to the negative 18th. All right, maybe that wasn't the best example. Oh, I think it actually, sorry guys, I think I typed in the wrong number here. Yeah, that's the problem. That's not the small. Hang tight here. I put 5 instead of 15. My bad. Like that can't be right. It is still a small number still. Let's see here. Hope if I did this right. All right, there we go. Sorry about that. 0.0785, which means approximately 7.9%. That seems a lot more reasonable. Okay, 7.9% chance you get 15 over 10 minutes. All right, now last question. I'm not going to attempt to do this one by hand, but you could certainly check the other two using your calculator if you want to. I guess we go ahead and check one of them. Doing the PDF, you do second distribution, Poisson PDF. Lambda would be 18. X value is 15. And you do get the same one, so check that off. Got the same answer. All right, now with the less than 10, so the probability of R, or you could say X, either one, is less than 10. So if it's a simple less than, we're going to be doing just our Poisson CDF. And if we check back there, less than is right here, right? So we're going to do a lambda, but our X value, we're going to subtract 1. Because when it does the CDF, it includes the value that you put into it. So if we did, we want to do 18, and then we actually want to do 9. Because if we did 10, then it would be including 10. But we want to know less than 10. So we want to basically say, what's the probability that it's 9 or 8 or 7 or 6 or 5 or 4 or 3 or 2 or 1? So we want to put 9 there because it will include that 9. If we put 10, it would include the 10, and that would not be correct. So let's go ahead and do that real quick. Again, I'm not going to do that by hand because that would take too long. So we want to do 18 as our lambda and then 9 for our X value. And we get 0.0153. So that would be 1.5%. So a very small chance that it would be less than 10. All right, let's go ahead and look at, I think I got 2 more here real quick. This is an easy one. All right, I don't know how accurate this stat is. I think it's a little bit old, but let's just say if Twitter has approximately 500 million tweets per day on average, what is the probability that in the next hour there are 30 million tweets posted? Okay. Now notice the difference here. When we're talking about lambda, it says 500 million per day. All right, so lambda equals 500 mil. Don't write out all the zeros, per day. 500 million per day. Okay. Now it asks what's the probability that there's going to be in the next hour. hour, there are 30 million. So if we're going from days, our question is in hours. So we actually need to divide this by 24 to get in hours. So we need to divide by 24, and then lambda is going to be 500 divided by 24 is 20.833 per hour. So it's important that we change the units there. Again, make sure you watch for that on your homework assignment because the units do change in most of these. All right, so approximately 20.8 million per hour. All right, and then we're asked the probability of 30 million. So probability of 30 mil. We can just leave it. Just type it in as 30s. Just know we're talking about millions when we write our answer. So the probability of 30 million. Well, that's going to be e to the negative lambda. So e to the negative 20.833. And if you wanted to be even more specific, the most accurate answer would be to not even type that, but to just type in negative 500 over 24. And that's how I'm going to type it in. So make sure we get all of our decimal places. And then lambda, so it would be 500 over 24 to the r. So r is going to be 30 over 30 factorial. So that would be the best way to type it in. I'm just going to do this one on my calculator. Go ahead and do the Poisson. So if you're just going to do it on your calculator, then what I want you to write out is Poisson PDF. And then just do parenthesis, write your lambda, which is 500 over 24, comma, your x value or your r value, which is 30. So if you are doing that on your calculator, you need to write either this or both. It'd be good to do both and check. So I'm going to go ahead and do it here. Poisson PDF. My lambda is 500 over 24. And my x value is 30. And I get 0.0123. So that is approximately 1.2%. All right, let's go and look at our last one. So Instagram, again, I'm not sure how accurate this stat is right now, but let's say it has approximately 95 million posts per day. What's the probability that Instagram will has more than 700 million posts in a week? So again, notice the unit change here. Lambda is 95 million a day, and our question asks 700 million posts in a week. So we need to change this to weeks. So lambda, well, if we have 75 million a day, 95 million a day, we're going to times it by 7. So 95 times 7 is going to give us 665 million per week. That's the average, 665 million per week. So then when we're calculating more than 700 million in a week. So more than. So more than means greater than. So more than that, probability that R is greater than 700 million. And actually, let me change the wording just so we get can experience every different formula here. So what I'm going to say, instead of saying more than, I'm going to say at least. If this were at least. So at least would imply 700 million or more, right? At least, I can't read that. At least would be 700 million or more, right? Because if it's at least 700 million, it means 700 million would be good, and anything greater than that. So 700 million or more, or at least 700 million, would be greater than or equal to 700 million, right? So if that's the case, well, we know we're going to do a 1 minus. Those are always complements for the greater thans. So 1 minus Poisson CDF, cumulative. We know lambda is going to be 665. And then let's think about if we need to type in that value or not. You can refer back to this cheat sheet deal if you want to. So if it's greater than or equal to, we do have to subtract 1 from the x value. So that's going to be not 700 million, but it's going to be 699 million. Because if we did 700 million, it would be subtracting out the probability of 700 million. we want to keep that 700 million, so we want to subtract out everything 699 and below. So what this is doing, this point, so on CDF, it's doing adding up all the probabilities 699, 698, 697, 696, all the way down to 0. It's adding all those up for us. Whoops. And so let's go ahead and type that in. 1 minus second Poisson CDF 665 and 699. And we get 0.0912, so approximately 9.1% chance. All right, so I hope that all made sense to you guys. If you are struggling with interpreting a particular question, feel free to just email or put it in the comments, hey, I don't understand what the R or the lambda is in this, and I'll help you with that. All right, good luck, guys.